Let's go ahead and do a conversion problem before we move on to density. So how many inches are in 8.42 kilometers? Okay, so it's a conversion factor problem or dimensional analysis problem. There's a couple different ways that you can approach it. So I'll let you guys mess around with it for about 3 minutes, and then I'll show you some of the most common ways that I see people solve it. Okay, so some of the flowcharts that I will see, or the thought process that I'll see with these is, sometimes people like to go from kilometers into miles. And that's sort of a relatively well-known conversion. And then miles into feet, and then feet into inches. Sometimes people like to go kilometers into meters, meters into centimeters, centimeters into inches. What other things have I seen? Sometimes people go kilometers into meters, and then meters directly into inches because they know the relationship there. Or sometimes people will do kilometers directly into centimeters using King Henry died before drinking chocolate milk, right? We just move the decimal over 5 hops. And then from centimeters, just go directly into inches. This, get as creative as you want within this narrow box here. So whichever one worked best for you. I'll do the first one. Let's do this first one, and I'll do this last one. So I start with my given information in kilometers, 8.42 kilometers. Now, setting it up in dimensional analysis, we're going to hop from kilometer to mile. And I know that 1 kilometer is equivalent to 0.621 miles. All right. That is a conversion factor that I believe is on your formula sheet. It's a pretty common one. This is why I don't like miles though, and feet and stuff, because 1 mile is 5,280 feet, not a well-known number. And then feet into inches, and I'm going to put feet on the bottom here. So 1 foot for every 12 inches. And the whole goal with dimensional analysis is that you set it up, the conversion factors, in such a way that each step, you're going to knock the unit out, top and bottom. The only unit we'll be left with is the inch, which is where we were headed, right? And in this case, we're just going to multiply across the top. And we should end up with a large number. 331,298 with some decimals. How many significant figures do we need to round to? We go with the given information. So the given information has 3 sig figs. Sig figs. So we want our final answer to round to 3 sig figs, which means the 3 and the 1 are significant. The 2 will tell that 1 to stay. So 3, 3, 1, 0, 0, 0 inches. Could write it in scientific notation as well. If the problem specifically asked for it, we would write it as 3.31 times 10 to the 5th inches. If you wanted to do this second method here, we have our kilometers, which is 8.42 kilometers. If I want to go from king to chocolate, I need to take 5 hops to the right. So I'm going to go 1, 2, 3, 4, 5, fill those in with zeros and give it the new unit of centimeter. Then I can go to the relationship that 1 inch is equivalent to 2.54 centimeters. The centimeters will cancel and you end up with the same answer. Okay, so different path, but same answer. You know, the number that it pops out is slightly different, 3. 331,496 centimeters. But still we're going to keep 1, 2, 3 significant figures, which would round it to 331,000 centimeters. So this information, remember this, and like this is sort of junk information because our given information wasn't super precise. That ringing bells on how to do dimensional analysis. You guys feeling okay with dimensional analysis? You're going to get more practice with it in your homework if you haven't done that. Questions on anything with that? Right, well, then we're going to move forward into the last little bit of chapter 2 here before we go into chapter 3. So we want to talk about this thing called density. And density is a physical property, meaning that a material exhibits this property without having to change what it is. So color is a physical property, density is a physical property, boiling point are physical properties. We'll get more into that in chapter 3. But why do some people pay $3,000 for a bicycle made of titanium? And they'll spend actually more than $3,000 on a bike that's made out of titanium or some sort of like fibrous carbon. And every semester I get people say, well, because the bike is lighter, right? Well, sort of. I mean, the bike does weigh less, but I could give you a bicycle that weighs less that's, you know, this big. That's like a tiny person bicycle, right? Or a Barbie bicycle. And that's not going to be very useful to you. So we want the bicycle to keep the same volume whilst also decreasing in its mass. So we're not actually getting a bike that weighs less. We're getting a bike that has a lower density to it. So we look like an iron frame is going to have a density of 7.83 grams per centimeter cubed. Density has kind of a funky unit, and then we get these double units. So we'll get a mass value divided by or over a volume value. So 7.86 grams in every centimeter cubed. So if I took a little cube of this metal, it would weigh 7.86 grams. Now, if I had a nicer bike made out of titanium, it's going to have a mass of 4.5 grams in that same volume per centimeter cubed. Okay, so it's not the bike. Yes, the bike is lighter, but the bike is lighter whilst also keeping the same volume. So here's our equation for density. Density equals mass over volume, or D equals M over V. 3 variables in this equation. This problem is, we're going to approach these a little different than the unit conversion dimensional analysis stuff. This is a plug and chug. Okay, so you will get 2 of the 3 and you solve for the third. You don't need to set it up in dimensional analysis. We're just going to do like algebraic equations. So if you have difficulty isolating variables, like you want to be able to solve for just mass on its own, right? And the way that we would solve for mass on its own is I'd multiply, or rather I'd divide this side by mass, and I would divide this side by mass, and the mass goes away. And then I get density over mass equals 1 over volume, right? I have to flip these or find the reciprocal of it. So mass over density is going to equal my volume. All right, if you have trouble isolating variables, here is kind of a nifty trick. So draw a triangle, and we're going to divide it into 3 quadrants or 3 sections. In the lower left-hand corner, I want you to put your D. On the top, I want you to put an M, and in the lower right, I want you to put a B. This bar here is a divider bar. Okay, so anytime you cross over that, you have to divide. This thing here is a multiplier bar. Anytime you move across that, you need to multiply. So if we want to solve for density, density is going to equal, right here, but let's read it off the chart, mass divided by volume. Mass divided by volume, okay? If we want to solve for volume, which is over here, volume is going to equal my mass divided by my density. And then if we want to solve for mass, okay, it's density times volume. Density times our volume. So that's a little way to isolate the variables a little bit quicker, especially if you haven't done algebra in a while. Now, because density is a derived unit, or it's made up of 2 other measurements, it is going to have a double unit to it. So some things that you'll see for density unit-wise will be like gram per milliliter or gram per centimeter cubed. Remember that a milliliter is equal to a centimeter cubed. Okay, so those things are interchangeable. So if I have, if I tell you, hey, it's got a density of 3.6 grams per milliliter, and I wanted to know what it is in centimeters cubed, it would be 3.0 grams per centimeter cubed. Okay, these 2 things are equivalent to each other. Sometimes you'll see units, grams per liter. A lot of times you'll see this with gases because they have such a low mass over a given volume. So we need to bump up the volume. So double units for our density. If we look at a problem here, so this says we calculate the density of a substance by dividing the mass by the volume. Okay, so we have a liquid sample and it has a volume of 22.5 milliliters and a mass of 27.2 grams. So now really start getting in the habit. You see that gram value, that's talking about mass. You see the milliliter, that's talking about volume. So gram on top, milliliter on the bottom. We're solving for density. The units won't cancel, right? Gram can't cancel with milliliter. So both units come back with us, and we want that. We want a double unit. So that 27.2 grams divided by the 22.5 milliliters will end up giving us a value of 1.21 grams per milliliter. And we bring both units with us. It's pretty simple. And when it comes to using this equation, it's not always that you're given mass and volume and you have to solve for density. Sometimes you're given, mass and density, and I want you to solve for volume. So let's actually go ahead and do that. So let's say, let's go. How many grams are in 185.2 milliliters of a liquid with a density of 8.47. It's a really dense liquid. Grams per milliliter. Okay, so how many grams are in 185.2 milliliters of a liquid with a density of 8.47 grams per milliliter? I'm going to have you guys attack that. Set your problem up. What's your given information? What are you trying to find? Isolate for the right variable, and then plug and chug. And we will meet back in, you use about 3 minutes for this. I have a question that says, do we have to line up the double unit in a specific order, such as grams before milliliter? Yes. The gram will always be the top. The milliliter will always be below the fraction bar. And this number is associated with the gram per 1 milliliter. So we don't ever want to say 8.4 milliliters per gram because the definition of density is mass over volume. Okay, so let's look at this one. So we're given two pieces of information. I know the density, which is 8.47 grams per milliliter. I also know the volume. All right, so this is density. Volume 185.2 milliliters is my volume. So I want to find mass. So using our little triangle over here, density, mass, volume, I know that mass is going to equal density times volume. So mass is going to equal this density times the volume. Check and make sure the units are all in the same page. So this is in milliliters, this is in milliliters, that looks good. So we can just plug it in as the two values multiplied by each other, 8.47 grams per milliliter. And I always write my units in. I don't just write the number. The unit gives me confirmation that I plugged it in correctly. And we're going to multiply this by 185.2 milliliters. So what happens here is the milliliter is sitting like above an inferred one here. The milliliter here is below this fraction bar. Anything above a fraction bar and below a fraction bar cancels. So the unit we'll be left with is a gram. And that just kind of gives me confirmation that yes, in fact, I want to be multiplying these two numbers together. We end up with a little bit of a larger number with some decimals, and we only get to use 3 significant figures. This has 4 sig figs. This has 3 sig figs. We're only as strong as our least precise piece of information. So I'm going to go with 1570 grams, 1,570 grams. Any questions on that? You can throw it in the chat. You do.
So I got 15,068.
Not sure why we multiplied these things instead of dividing anything. And we're going to do one more of these density problems. Let's try. How do I want to do this? How much space does 48.07 kilograms of a solid with a density of 18.42 grams per milliliter take up. So this is a pretty heavy or rather dense material. It's probably a heavy metal like mercury or platinum. So I want you to figure out space, and space being synonymous with volume. I'll give you 3 minutes for that. Okay, so Cynthia, I saw your question, so we'll just answer it as we go along. When working on this problem, I'm seeing this word density, right? So I know I'm going to probably use density equals mass over volume. I have given information. I know that I have 48.07 kilograms. I also know that the density, this is the mass, density is equal to 18.42 grams per milliliter. So I want to find volume. You should get that volume is equal to mass divided by density. Some people get, volume equals density divided by mass. No, definitely not. So make sure you're isolating correctly. Now, if you were to plug this directly in like this, hopefully you would add the units, and that would be kind of a blocker for you to stop and rethink. So if you were to go 48.07 kilograms divided by 18.42 grams per milliliter, you would realize, oh, this is a gram, this is a kilogram. I'm missing something here. These aren't matching up. So we can't plug this in like this. We have to have the units match up. And this is such a simple equation that, these are little ways that I'm going to test your skills. So just always be double checking and making sure the units match up before you plug them into an equation. So this is in kilograms, this is in grams. I'm going to convert kilograms to grams. Some people say, well, can't we convert the density into kilograms per milliliter? You could, but I say if there's double units, I leave that one. I go for the single unit. So we can multiply this by 1,000. We can move the decimal over 3 places, and we end up with a new number of 48070 grams. Now we can plug this into our equation. 48070 grams divided by our density, which is 18.42 grams per milliliter. Grams will cancel, and anything below a division bar and below a second division bar or divide becomes a multiplier, or it goes back up on the top. So we'll have a unit of milliliter here. When we plug this into our calculator, I got 2,609.66. We get to have 4 sig figs, 1, 2, 3, 4 there, and 4 there. So we'll go with 2609. The 6 tells the 9 to round up. So it would be 2610 milliliters. And I'm going to put a decimal there to let the reader know that that 0 is also significant. So yes, make sure your units are matching up. If the problem doesn't explicitly say what unit it wants it in, just give it the unit that it pops out in. So it popped out in milliliters. But let's say the problem instead said how much space in volume in liters. If it wanted us to convert it to liters, we could move the decimal back 3 spots, and it would be 2.610 liters. Which isn't a very big volume, right? 2.5 liters roughly. So it's not a huge amount of space. Why isn't it that big of a space? Because this thing is like super dense, right? So a decent amount of kilograms of it isn't going to take up a huge space. Questions on that or on density and how to solve density problems? Okay, so then we'll leave density because we solved it for each variable. Just make sure, you're checking for units when you do these. Okay, so that's the end of chapter 2. You guys finished a chapter. Congratulations. So just to clarify, we will cancel a double unit in the equation each time. It depends on what you're solving for. So if you're solving for density, you will have 2 units, one over the other. If you're solving for mass, you should only end up with the unit of gram. If you're solving for volume, you should only end up with the unit of milliliter or centimeter cubed. It's really dependent on what you're solving for. Density, double units, the other one, single units. Okay. By chapter 2. Oh, real quick. Here's a list of some common densities. The one density you just want to know is water. Water has a density of 1, so not that hard to remember. And the unit on that is gram per centimeter cubed. So 1 gram per centimeter cubed, they've sort of, fashioned all these other things off of that. Things that have a lower density than that, like ice, ethanol, charcoal, oak, wood, those things will float in water, right? You could make a density column where more dense things will sit lower, less dense things will sit higher. Up from water, glass 2.6, that's got twice the density. And then we start to see these like heavier metals. So copper, lead, gold, platinum, super, super dense. All right. Goodbye, chapter 2. Hello, chapter 3. Chapter 3 is all on matter and energy. If we were to think of like the universe, okay, we've got the universe and that's all this giant void or space. It is filled with material, matter, and then it is filled with like a force that does something to that matter that allows it to have movement, allows it to have creativity, it allows it to change and transform, and that would be our energy. So atoms and molecules, or this thing called matter, is all over the place. There's different kinds of matter based off of what the atoms are, right? If I've got a bunch of carbon here in this golf club, we will have certain properties. Over here in this water bottle, there's H2O, or water molecules, and that has a different set of properties. The properties are based off of what the atoms are. So how do we define matter? Well, it's going to be anything that has both space or occupies both space and has a mass. So if it doesn't have mass, we cannot classify it as matter. Now it can have a very small amount of mass, but it has to have something. Some types of matter that are really easy for us to associate with matter, things that we can see. So like the desk sitting in front of you, the computer, your body, right? These are all made out of matter. There's mass and it's occupying space. There are a lot of things though out there that are composed of matter that we can't perceive. We can't see, we can't taste, we can't touch them. They're too small or they're too low density for us to notice. Things like that could be air, dust, individual particles or atoms. Just because we can't observe them doesn't mean that there isn't matter there. From a human scale, because we're such like egotistical creatures, we kind of always think of things on our scale. So from our scale, when we interact with matter, it appears very continuous or smooth. So like the desk that you're working on, or the bed that you're working on right now, it feels smooth, it feels consistent. But matter is actually, when we break it down into its fundamental parts, is composed of these tiny things called atoms, or composed of these little packets called molecules, which are multiple atoms bonded together. And they're made up of these atom molecules and then space. So it's really actually quite discontinuous when we see it on a microscopic scale. There's a lot of like kind of clumping together of things and then space, and then clumping together of things in space. So I'm going to skip forward really quick because, no, not yet. We won't skip forward just yet. So atoms and molecules are the basic unit of matter. All matter is ultimately composed of atoms. Over here, I have an aluminum can. It's composed of a bunch of aluminum atoms. The simplest form of this would be one aluminum atom. The atoms exist sort of as independent particles that are stacked together in a crystalline form. Now, when we're dealing with a compound's simplest identifiable unit is a molecule. So this here is rubbing alcohol or isopropyl alcohol. We have these little isopropyl alcohol molecules. Now, when we have a compound like this, it can be broken down into its simplest form, which is an individual molecule. And then that molecule can actually be broken down into something simpler, the individual atoms that it's composed of. An element can't be broken down into something simpler and identifiable. So there are 3 common states of matter that we're going to be working with: solids, liquids, and gases. So on Earth, we find things in all 3 of these states. There is a 4th state, plasma, that we won't spend any time on. We interact with plasma in very rare situations on Earth. You can see plasma when you see a lightning strike or something like that. But out in the ethers of the universe, there's lots of plasma out there. But for the sake of what we're dealing with today, solid, liquid, and gas. Water is a really unique material in that at Earth, we can find it in all three states. So ice would be its solid form, water would be its liquid form, and then steam, maybe around like a steam vent or volcano or hydrothermal activity, would be its gaseous form. In ice, or the solid form of water, the water molecules are really close together. And the adjacent water molecules will have a mild amount of vibration, but not enough vibration that they break apart from each other. So they have a fixed position, or they're kind of fixed relative to each other. So you can think of a solid as like a bunch of soldiers lined up in a row, and they know their place and they're facing forward, and that's their position. In a liquid, or when we're dealing with water, the water molecules, and I mean, how do we go from a solid to a liquid, or how would we go from ice to water? We would apply heat, right? So we add some thermal energy. And so we increase the thermal energy, and the adjacent water molecules start to vibrate a little bit more. And they'll vibrate to a point where they're no longer fixed next to each other, but they'll begin to roll past each other. Okay. So in a liquid, the particles are still really close together, but the particles are allowed to now move past each other. They have enough energy to do that. And that's what gives liquids their ability to flow. In a gaseous form, or steam, there's so much thermal energy pumped in that these particles have lost their intermolecular attachment, or their kind of stickiness to each other, and they spread out and form like a really, really big space, very low density or gas. So here are all those soldiers in a row in a fixed position in this nice solid crystalline form. Here we've added some thermal energy. These soldiers, you can say, like we've given them a little bit of alcohol. So now they're like kind of casually chatting with each other. And then over here, it's gotten really hot outside, so the soldiers have like spread out from each other. And this happens through an increase in thermal energy. This happens through a cooling process, or pulling thermal energy out of the system. So some things that go along with this: when you're in a solid state, the matter has a fixed volume and a rigid shape. So if I take an ice cube out of the ice cube container, ice cube tray, and I put it in a glass, does the ice cube change shape? No, it stays that same square shape, and it stays the same volume. Ice, diamond, quartz, iron, they're all examples of solids. Most of the metals that you see on the periodic chart, or the things on the left side of the periodic chart, are solid form. There is one metal that is not solid at room temperature, and that would be mercury. So we can narrow down a solid to be either what we call a crystalline solid or an amorphous solid. A crystalline solid is just what it sounds like. It's very linear, geometric. There's a long range pattern or order to it. Lots of times our salts, and when I say salt, that's a general term for a metal combined with a non-metal. And we'll explore that a little bit more in a couple chapters. But anytime we have a metal and a non-metal combined together, they form this really nice long order. Diamond as well. A lot of things that show macroscopic order. So like a diamond forms a crystalline shape, or table salt will form crystals, usually also has microscopic order as well, or this long range order. An amorphous solid, on the other hand, doesn't have this long range order. Amorphous solids are like glass and rubber and plastic. They are in solid form. The adjacent particles or atoms are fixed in their position. They just happen to not be facing the same direction. They're not as neat and clean. Here is sodium chloride, which is table salt. Again, on the macroscopic scale, or the human eye scale, that has this really like pretty crystalline shape. That is indicative of the long range order that we're seeing on a microscopic scale. So a sodium and a chlorine, and a sodium and a chlorine, over and over and over again. A liquid. So with a liquid, we've added thermal energy, and the particles have started to vibrate to the point that they are moving past each other now. They're still close together though, so I can't compress a liquid, or the volume of a liquid stays the same. But the shape can change because the material can flow. So if you have 100 milliliters of water in a cup and you pour that into, say, a beaker, it's still going to be 100 milliliters, but it will change shape, and that it'll now spread out to the size of the beaker, right? If you were to take that beaker and pour that water on the floor, that water would spread out to sort of create a big, broad, thin layer of water across the surface of the floor, but it would still be 100 milliliters. So water, gasoline, alcohol, and mercury at room temperature are all examples of liquids. Now, the last state of matter, gas, which gases are super cool. They do really cool things. And we actually will spend an entire chapter talking about gases. In a gas, there's so much thermal energy that the particles have spread. They're not just moving past each other, they've spread away from each other. And they've spread away from each other so far that there is no more interaction between the particles. So you can kind of think of the particles like billiard balls, like just kind of moving through space. And they'll randomly maybe ping pong into each other and then move in the opposite direction, but they're not clumping together. And because there isn't any attraction or they're not clumping together, they just sort of drift away from each other. And so because of that, gases will always assume not only the shape of their container, but also their volume. So they stretch out. So if I had a container of compressed gas and I opened that in this room, that compressed gas would enter the room and spread out until it filled the entire volume and shape of the room. And because they can change volume and shape, we can compress a gas. We cannot compress solids and we cannot compress liquids, okay? But we can compress a gas. At room temperature, things like oxygen, helium, and carbon dioxide are all examples of gases. Carbon dioxide, it can be a liquid though, and it can also be a solid. You guys may have interacted with carbon dioxide in solid form. It's called dry ice, okay? So if you ever get those like Blue Aprons or the fresh foods or whatever, they always put like a big hunk of dry ice in there, and they're super fun to play with. It sublimates, which means that it goes directly from a solid to a gas. You won't see it in liquid form. That's why it looks like it's smoking, because it's moving from the solid to the gaseous state. Fun to play around with, but be careful. Don't ever touch it directly with your skin and stuff like that, because it can give you a pretty bad burn. So if we had two pistons over here, this piston is filled with a solid, or this could be a liquid. There isn't any room for the piston to move down. Now in a gas, there's so much space between these particles that we can compress that gas down. You guys interact with compressed gas on a daily basis, I'm sure. Whipped cream, that's like, I don't know why that's where I went, and that's all I can think of is whipped cream, but we've got whipped cream. Like anytime you use aerosols, hairspray, stuff like that, these are all compressed gas. So this chart kind of gives us a full summary of what we just talked about. You want to know this. I mean, I could say, hey, what material is not compressible but takes up the shape of its container? That would be a liquid, right? So know these, or which one has atoms close together and has a fixed shape and volume? It would be a solid. So, okay, yeah. So before we get into this, I want to skip forward because I like this. I don't know why they don't put the drawing first, but this is how we're going to organize matter. So at the very, very top, we first classify that it's matter, which means that it has mass and it takes up space. Then we're going to divide it into being either a pure substance or a mixture. Okay, so go ahead and write that down, pure substance or mixture. For a pure substance, we can separate that into being either an element or a compound. And a lot of times people get compound and mixtures mixed up. So we will go over what those mean, but definitely don't interweave these two together. If instead of being a pure substance, we were in fact a mixture, we could divide our mixtures into being either homogeneous or homogeneous, or a heterogeneous mixture. So kind of 4 different categories at the very end of how we can define matter. So let's go back and go through each of these things and what they mean. So when we're talking about a pure substance is something that's composed of only one type of atom or molecule. Okay, so aluminum. Or water that's just got H2O. One very specific thing to it. A mixture, on the other hand, is going to be composed of 2 or more different types of atoms or It could be two or more different types of molecules that aren't fused together, and we can adjust the proportionality of it. So like salt water, for instance, is NaCl salt and H2O water. I could add more salt or add more water and change the proportionality of it. So pure substances are more definite, more specific. Mixtures have more variability to them. So if we're looking at a pure substance, the first one is an element. So a pure substance that cannot be broken down into a simpler identifiable substance. I want to say that, a simpler identifiable substance. So like if I took carbon and I had a carbon atom, I can't break that down into anything simpler that's also still like identifiable and unique. I could break it down into protons, neutrons, and electrons, but the protons of carbon are the exact same as the protons of hydrogen. You wouldn't be able to tell the difference. So the smallest or the most basic identifiable thing is an atom of an element. No chemical transformation can decompose an element into simpler substances. What are the elements? There's about 118 of them, 120, depending on what periodic chart you're looking at. So you look at a periodic chart, all those things are examples of elements. Lithium, hydrogen, carbon, oxygen, sodium, all elements. We don't interact a whole lot with elements in everyday life, pure elements. Most of the time, so here, here's a helium balloon, assuming that this was like a perfect seal and there wasn't air in there before, we just have helium atoms in there. But we don't really deal with elements in their element. We don't deal with them in their elemental form on a regular basis. Most of what we interact with are compounds, because elements on the periodic chart are relatively unstable. So they want to pair up or bind with something else to create some stability. And we will get into how they combine and all that stuff later. But for now, most of the things, you can just know most of the things that we deal with are a compound. And a compound is when we have two or more elements that are fused together and they have a fixed proportion, which means I can write a chemical formula for them. So examples of a compound: H2O, okay, NaCl. C11H12, I'm sorry, C11H12O22, sugar. So we've got all these things and they have a recipe. I can't change the proportionality of hydrogen to oxygen. Okay, it's got to be 2 hydrogens for every 1 oxygen. That is what makes water water. Otherwise, it would be something else. Compounds are a little bit different than elements in that I could technically break a compound down into simpler things. I could take these compounds and I could break them down into elements, right? So I could take water and break it down into hydrogen and oxygen. It has the capacity to break down into something simpler. So here we've got a pure substance of water molecules, 2 elements in fixed definite proportions. Doesn't matter how big the sample is, whether it's 1 water molecule or it's a bathtub full of water molecules, it will always have this 2-to-1 hydrogen to oxygen ratio. That's what gives water its properties. So the difference between a pure substance and a mixture, because a mixture is made up of 2 or more things, but instead of them being chemically bonded or united together, they're just mixed together. Okay, so a compound, they're fused together, like 2 hydrogens and an oxygen. They make a water molecule. In a mixture, it would just be like, a mixture would be, hey, I've got hydrogen gas and oxygen gas floating around in a balloon together, right? They're not fused together. They're not H2O fused as a molecule. This is a diatomic and this is a diatomic floating around in a balloon together. So some examples of mixtures, we talked about salt water being a mixture. So that's water with NaCls dissolved in them. The salinity of the water can change. We tend to have warmer, saltier water at along the equator, right? More salt can be dissolved in there. The atmosphere is also an example of a mixture. A lot of times people will think of air, they'll go, oh, that's an element, it's oxygen. Well, there is oxygen in the air, but actually the larger proportion of air is made out of nitrogen. So we've got oxygen, nitrogen, argon, carbon dioxide that you're breathing out, and maybe some traces of other things as well. So dividing our mixtures down farther, we can call them either homogeneous or homogeneous mixtures and or heterogeneous mixtures. Homogeneous, the root here being homo or the same. A homogeneous mixture is something that's evenly mixed throughout. So sweet tea. If you have sweet tea, unless you've added so much sugar that it's precipitating out of the bottom, that is too much sugar, okay? That's too much sugar for the sweet tea. But as long as you haven't done that, the sugar should be evenly mixed throughout, right? The sweetness on the top and the sweetness on the bottom will be the same. A heterogeneous mixture, on the other hand, hetero being different or opposite, that's when we have a material that isn't evenly mixed, or depending on like where you sample it, you'll get different quantities. So hydrocarbon in water or oil in water, you know, oil and vinegar dressing, what happens to the oil? It always sort of sits on the top. Even if you shake that thing up for days, you still will get like little beads of oil because it isn't an even mixture. Another example of a heterogeneous mixture, like spaghetti and meatballs. Okay, so the spaghetti and the meatballs, they're all in the plate together. But depending on like what your perfect bite is, maybe it's more meatball and sauce and less spaghetti, or more spaghetti and less sauce and meatball. That would be a mixture that is not evenly mixed throughout. Now, if we took our spaghetti and meatballs and stuck it in a blender, like a Vitamix, and just like totally blended the crap out of it, I guess we could maybe turn it into a homogeneous mixture and then drink it. That'd be disgusting. But right, there's a difference here. And that a homogeneous mixture evenly mixed throughout. A heterogeneous, you'll see it. You'll see that there's some sort of like difference in the mixture. Cereal with bananas in it would be a heterogeneous mixture. So I'm going to give you a couple things. I want you to tell me what they would fall under. Okay, so let's say we have lithium sulfate, Li2SO4. And if you're like, I have no idea what that is, you don't have to know what it is, but you do want to be able to classify it right now. So what is this thing? It's a chemical formula. If it can have a chemical formula, we're going to call it a compound. What about aluminum foil? We would want to classify that as an element, assuming that it's pure aluminum, and we're going to assume that it's pure aluminum. That would be an element. Brass. Brass is a combination of zinc and copper. This would be a homogeneous mixture. Not all mixtures are liquid. Okay, sometimes mixtures can be two solids mixed together or two gases mixed together. But if we had something that was made out of brass, right, these two things should be equally mixed together. What about mac and cheese? Cheese. It's definitely not a compound, okay? There's no chemical formula for mac and cheese. Depending on how you like your mac and cheese. Maybe you like it cheesier. Maybe you like it with more butter or milk. So we're going to say that this is a heterogeneous. So this thing here, elements, there's only 118 or so of them. Compounds, totally a lot of them. Yeah. Mixtures, lots of mixtures. You can make all sorts of mixtures. Okay. So if we have some sort of matter, now we know we can classify it as being a solid, a liquid, or a gas, and then we can also decide if it's an element or a compound or a mixture. We also want to talk about properties. So depending on what that material is, if it's water or if it's, carbon or if it's just any of those things, it's going to have different properties. And you can have physical properties. Hi. Grayson, is that your little one? Hi. You want to learn chemistry with us? Hi. So we can have physical properties or chemical properties. A physical property is a property of a material that displays itself without having to change like its composition or what it is. So color, hardness, luster, density, boiling points, all these things, the sublimation point, freezing point, those are all physical properties. Like a ring doesn't have to become, like a gold ring doesn't have to become something different in order to show you that it's gold. That's just sort of an innate property of it. So we would say that's a physical property. A chemical property, on the other hand, is something that you can only observe or see if the material itself changes. So let's talk about gasoline. Gasoline, the odor of gasoline is a physical property. If you spill gasoline on your hand, the gasoline isn't having to become something new for you to smell it. It's just turning into a gas and then it's hitting the receptors in your nose. A chemical property of gasoline is its flammability. How does gasoline show you it's flammable? Well, you have to like light it on fire and it has to convert into something new. So you would get carbon dioxide and water and a bunch of heat. And we capture that heat from gasoline to run our cars. So yeah, the odor of gasoline is a physical property. The flammability of gasoline is a chemical property. Any phase changes are a physical change. So when we go like boiling point, freezing point, anytime we're going from a solid to a liquid, liquid to gas, gas to solid, whatever it happens to be, the material may look different, but it isn't a new thing. The boiling point of water is a physical property. It happens at 100 degrees Celsius, and the water isn't changing what it is on a molecular level. It may look different, but it's still H2O molecules, right? Down here in the coffee pot, it's liquid H2O. Up here, it's just gaseous H2O, but there's still little H2O packets. I haven't changed what those things are on a molecular level. So any state changes, transformations from one state of matter to another, are always physical changes. And that can be tough sometimes for people to accept because sometimes physical changes or transformation in phases can look so dramatic. Like iodine, for instance, on the periodic chart, when it is a solid, it is like a gray, dull metal color. When it is a gas and it likes to sublimate when you heat it, so it turns directly from a solid to a gas, it turns this bright pink purple color. And people see that and they're like, oh my God, that must be a chemical change. But it's actually not. Both of them are iodine. They just happen to have very dramatic different appearance in different phases. So along with that, in a physical change, matter changes its appearance, but it's not changing its composition. So that shift from iodine going from a solid to iodine going to a gas, it's changing color, but we would still just classify that as a physical change. Another one, when ice melts, it looks different, right? Ice and water look different from each other, but they're not different on a molecular level. They're still H2O molecules. Now, in a chemical change, matter will change its composition. So it actually is one thing to start with, it undergoes the chemical change and it's something different. If you ever had copper and it's patinaed or it's turned green, same thing if you have like silver and it's like tarnished, or let's say you have a nail, an iron nail, and it rusts. Those are all examples of a chemical change. Those metals are interacting with the oxygen around them, and they're pulling that oxygen in to form a metal oxide. So the new material that you have is actually different from the starting material. So looking at this here, hello. We've got our now, and up at the top, we have the part that's not rusted. It's just a bunch of iron atoms lined up. Now, in general, most things don't like to exist in elemental form, so they will kind of react. So this thing will start to pull oxygens out of the air and form this iron 3 oxide. Now, here we had just iron. Here, I've got iron with oxygen. It's a new material. It's a new compound. So if you are, if a material is undergoing a chemical change, we would represent that using a chemical reaction. And I'm going to keep chemical reactions really simple for right now. We will spend a whole chapter on chemical reactions later on. But for now, it's going to look something like this. You have reactants on the starting side. You read it like a book, so left to right. On the left side, we have our reactants, which are the things that are reacting. You have to have one. You could have more than one. You can have 2, you could have 3, you could have 100. Products will go on the right side. You have to have at least one, but you could have a lot more. And then there's going to be an arrow that separates those two. And the arrow signifies a chemical change. Sometimes there's additional symbols up here, like little element symbols that let you know that there was a catalyst, or a little delta symbol to let you know that there was some sort of heat involved. But the arrow in and of itself is just letting you know that reactants have turned into products. So an example of a chemical reaction, there are, again, thousands and thousands of chemical reactions. But a simple example of one is the combustion of methane. So we take methane, which is CH4. Don't get freaked out if you don't know that's methane. That's okay. Combined with oxygen, which is O2. And don't get freaked out if you don't know that it's a diatomic molecule. But it produces water, and it produces CO2. And then I'm going to balance this thing. I'm going to put a 2 here and a 2 here. So these two things over here would be your reactants. CH4 and the oxygen. These two things over here are your products. Do these things look different than these things? Yeah, they should. The chemical formulas should change. If they don't change, it's not a chemical reaction. There's so many different chemical reactions out there. I could have, sodium combined with chlorine to produce sodium chloride. Balance that out. You can have the decomposition of water, H2O, breaks down to form hydrogen gas and oxygen gas. Right? There's like just so many of them, but just get in the habit of these are your reactants. This is your product. Okay. I feel like we're beating a dead horse with these things. Let's say we have a butane lighter. If you've ever messed around with a butane lighter and you just push down on the plunger, but you don't actually strike it. Sometimes you can smell the gas coming out. That would be a physical change. We're vaporizing the liquid. So we're taking the liquid and turning it into a gas, but it's still butane. So it hasn't changed what it is. But if we take that same lighter and not only do we push the plunger down, but we also strike it, then we actually take these this butane and we start to combust it, which means that we form heat, which is what you light your candles or whatever you're using it for with. And then we produce CO2 and H2O, which is a different material altogether, right? So these little guys look different than their original compound. Physical changes can usually be undone through distillation or filtration paper. I'm not super stressed about that. This is something that's important to know, the law of conservation of mass. So there is no new matter. or matter is neither created or destroyed when we're undergoing a chemical reaction. So the number of like aluminum atoms that you're starting with should equal the number of aluminum atoms that you're ending with, or the mass that you're starting with should equal the mass that you're ending with. This isn't always true for things like nuclear chemistry. We can get large quantities of mass changing directly into energy, and it appears that the mass is disappearing. It's not, it's just shifting to energy. But we aren't doing nuclear chemistry for this class. You may do nuclear chemistry in 130 and 151, but for the sake of this class, we're going to go with the law of conservation of mass because we deal with chemical reactions only, which says the mass you're starting with should equal the mass you're ending with. So here's an example. Suppose that we burn 58 grams of butane in a lighter. It reacts with 208 grams of oxygen to form 176 grams of carbon dioxide and 90 grams of water. You don't need to even know what these formulas are. You could just write butane is combining plus oxygen. The word problem here says to form. So that's our arrow. Anytime you see the word to form, to produce, to create, that's the arrow. And then it says it has 176 grams of carbon dioxide, 90 grams of water. These two values on the reactant side total 266 grams. These two on the product side also need to equal 266. That's the law of conservation of mass. We may be switching around the arrangements of the atoms, but we're not like matter isn't just disappearing on us. Okay, that would be strange, very strange if that happened in a chemical reaction. So let's say I want you to do one of these. How much salt is made when 33 grams of sodium combine with 18 grams of chlorine? And salt is sodium plus chlorine, just so you know. Sodium plus chlorine, or it's called sodium chloride. This isn't rocket science, okay? This is simple problem. So if I was to write like a basic equation for this, I would say, I don't even have to know the symbols or anything like that, but it's saying sodium combines with chlorine. Okay, so I've got sodium and it's combining with chlorine. And it's going to make salt. So how much salt do we get? Well, it says that we have 33 grams of sodium and 18 grams of chlorine. The reactants and the product side need to total each other. So as long as it's assumed that we're using all 33 grams of the sodium and all 18 grams of the chlorine, we're just going to add those two together, which gives us 51 grams as our total. So what does our total have to be on the product side? It also has to be 51 grams, right? We can't lose material in that process. So the amount of salt that we produced was 51 grams. Okay. So within the universe, we have matter, which is all the stuff. But if we just had the stuff, it would be really, really boring because the stuff wouldn't do anything. It wouldn't change, it wouldn't move, it wouldn't interact. So we need something else, kind of the umph to the universe, and that's energy. And energy is a huge component of the universe. It's harder to see energy. Usually we see the effects of energy or the secondary qualities of energy. And what is energy? Energy is the capacity for something to do work. And when I say the word work, I mean that not in like a layman's terms, but I mean that in a physics sense, where work is the result of a force acting over a given distance. Now, when you go to work, that is work, right? You're exerting yourself. So you are actually exerting energy over a given distance. The behavior of matter, and that's all types of matter, are going to be driven by energy. If we didn't have energy, matter wouldn't do anything. It'd be super boring. So we need to understand our energy in order to understand chemistry. And just like the law of conservation of mass, we also have this thing called the law of conservation of energy, which states that energy is neither created nor destroyed. The total amount of energy that's there is constant, but this energy can be changed from one thing to another. So energy can be transferred from one object to another object. This happens if somebody came up to you and pushed you. They would be taking nutritional energy, potential stored energy in their body, turning it into kinetic energy, which is movement energy, and they'd push you, which would then convert the movement energy into your body. Energy cannot be created out of nothing, and it doesn't disappear into nowhere. So that's why, perpetual motion machines are not something that we can come up with, because there's always friction. There's always a decrease in energy due to these different sorts of transfers. So I mentioned a couple of these, and there's a bunch of different types of energies, but these are the ones that we will see most often. Kinetic energy is the amount of energy, or is the energy associated with movement. So it's directly related to the velocity of an object. If you have a ball, if I threw a ball at you, it probably wouldn't hurt. But if there was if you had a ball chucker and you threw it at somebody, it has a higher velocity. So it's going to have more energy to it. Can you guys hear my daughter screaming? No. Okay. It's really loud. Potential energy is the energy that is associated with you kind of think of potential energy like stored energy. It's the energy that's associated with either a material's composition or its position. So you on the ground don't have a lot of potential energy. You up in a tree have a lot of potential energy because we have this thing called gravity, right? So it will pull your body down. That potential energy could turn into kinetic energy if you lost your footing and you fell from the tree and then you hit the ground. When you hit the ground, your kinetic energy, or the movement of your body, would actually turn into thermal energy. And thermal energy is, when you hear the word thermal and you think of temperature and heat, that's exactly what it's talking about. It's the energy associated with the random motion of atoms in the molecules. So when you hit the ground, you kind of shock thermal energy into the ground. So you create a little bit of heat in the ground. And if you're like, I don't think I produce heat when I fall out of a tree. Well, you're not moving very, very fast. And you also don't weigh that much. Think about a meteorite hitting the Earth's surface, right? That's moving much faster and it's much heavier. It has a lot more kinetic energy. It creates more thermal energy. We also have chemical energy. Chemical energy is a type of potential energy associated with the position of particles within a material. So like TNT, for instance, has a really high chemical energy. Because of the way that the atoms are structured in TNT, it wants to explode. Certain foods have more chemical energy than other foods. They have more calories to them based off of how they're structured. Fats tend to have a lot more chemical energy than carbohydrates. And then we have electrical energy. This is the energy associated with flow of electrical charge. I don't really spend a whole lot of time with that, so do what you will with it. So as far as how we measure energy, the SI unit for energy is the joule. It's a capital J, named after some dude named James Joule. And we will use joule quite often. We also have a second unit of energy, which is called a calorie. Make sure you are separating big C calories and the little c calories. Okay, do you see how this is a lowercase calorie? And then down here, we've got a capital C calorie, and they look so similar. They're not the same thing though, okay? The big C calorie, this thing here, that's a nutritional calorie. When you think about like a candy bar and what's on it, that's this thing here. A little C calorie is the amount of energy required to raise the temperature of 1 gram of water 1 degree Celsius. This is a larger unit than a joule, but it's 1,000th of a big C calorie. Sometimes the big C calorie is also called a kilocalorie. We call it a kilocalorie. Why do they call it a kilocalorie? Because it's 1,000 of these little C calories. So you're going to want to be able to convert between these units. We also have the kilowatt hour, which is 1 kilojoule per second times 360 seconds in an hour. This is a value that you would see on like your electric bill. And I don't do a whole lot with the electrical energy, so I'm going to stick more with joules and calories. Oopsies. Okay, so here is your conversion factors for energy. Notice that big C calorie does not relate to joules. Big C calorie relates to little c calorie, and then little c calorie can be switched to joules. So it's like a two-step problem. So write these two top conversion factors down if you don't have them. We're going to go to the next slide. I'm going to have you do a conversion factor for these, or unit conversion. Okay, so let's say we have a candy bar, and the candy bar contains 225 nutritional calories, or big C calories. How many joules does it contain? Now, this is not anything revolutionary. This is just unit conversions, dimensional analysis. It's the same thing as like converting from inches to feet. You just have different conversion factors. So I'll go ahead and give you all 3 minutes to work on that. And we'll come back together and we'll talk about how many joules are in that candy bar. That must be a small candy bar if it only has 225 calories. All right, so we have a candy bar, 225 big C calories. That's our given piece of information. We're trying to find joules. So if I make like a solution chart or a flow chart, I want to go from big C calorie into little c calorie, or a nutritional calorie into lowercase calorie. Then from there, I'll go into joule. Right, the relationship here is that 1 big C calorie is equal to 1,000 little c calories. On this one here says that 1 little c calorie is equivalent to 4.184 joules. So it's a two-step problem. So start with the 225 big C calories. I know that for every 1 big C calorie, I get 1,000 little c calories. Why do I put the big C calorie on the bottom here? Because I want those to cancel, right? That will get me out of this unit into this unit. Then from there, I want to go into joules, which is this relationship here. Because the little c calorie is on top here, I want to put the little c calorie on the bottom, because in the second step, I'm trying to get out of this and into this. We want joule on top. Give the appropriate value. So 1 of these for every 4.184. And the little c calorie will disappear, and we'll be left with just a unit of the joule. And then I let the dimensional analysis tell me what to do. So it says take the 225, multiply it by the top. I don't know why I put 100, guys. Let's make that 1,000. Okay. Times 1,000. So times 1,000. And then times that 4.184. Some people use 4.18. That's fine as well. I get a big number. I get gonna write it down here, 9,041,400 joules. I have 3 significant figures. So I need to round to 3 significant figures. So I'm going to round this to 941,000 joules. If I was to write it in scientific notation, 9.41 times 10 to the 5 joules. Okay, so a lot of joules in a nutritional calorie. Nutritional calories have quite a bit of energy to them. Any questions on that? The concept isn't different. It was just a new conversion factor. We're going to see that throughout the semester. You guys are going to see new conversion factors pop up all the time. So, yeah, okay. So potential energy, if we have a weight and you bring it up the stairs, so you use the potential energy that was stored in your food, you turn it into kinetic energy and you strongman the weight all the way up to the top. And then what you've ideally done is you've taken the kinetic energy in your body and you've transferred it into potential energy by pushing that weight against the force of gravity or lifting it up. And that weight can then get dropped, and that potential energy can shift into kinetic energy or movement energy. And then if that weight hits the ground, it will transfer that kinetic energy or that movement energy as thermal energy or heat. So we have this process of energy transferring constantly throughout the universe. When you have something with potential energy, it tends to be sort of unstable, right? This weight here is in an unstable position. We wouldn't want it to hang out there. Things like to move from unstable states or high potential energy towards low energy or more stable situations. So TNT wants to explode. Like that's where it wants to go. It wants to become a more stable version of itself. So systems with high potential energy do have a tendency to change towards lower potential energy or to create some sort of stability. So depending on your chemical reaction, if the chemical reaction is giving off heat or if it's giving off energy, that's known as an exothermic reaction. Exo, exiting. So energy is being released into the environment. If you're releasing energy, that means that the reactants will have a high amount of energy. Hold on one second. So when we look at these two diagrams over here, this top one is an exothermic reaction. Here's on the x-axis, they have energy, high energy, low energy. The reactants have a high energy. They release energy so that the products or what you're producing has a lower energy. This is like the combustion of methane. Our products will have a high amount of energy. We will drop that down to water and CO2, and the energy released is what we capture to run our car or to light a candle or whatever. But everything in the universe can't be an exothermic reaction. There has to be something equal and opposite to balance that out. So we also have these things called endothermic reactions, and an endothermic reaction is a reaction that absorbs energy from the surrounding environment. So in that case, the reactants have a low energy, and when we combine those things together, they will steal energy from the environment around them to produce products that have a higher energy. If you guys have ever used those instant ice packs, those like for injuries, where it has like a bag and then there's a bag inside of it and you have to break it and then they combine together and all of a sudden it gets really, really cold. That cold feeling is an endothermic reaction happening. And the endothermic reaction is literally sucking or stealing heat from the environment. And if you put it on like a swollen knee, it's pulling the heat out of your knee, out of your body.